Well, thank you very much, Stefan, for a very nice introduction. And I want to first thank the conference organizer and the scientific committee for this opportunity to present here. It's truly a great honor and pleasure to visit the beautiful city of Graz and enjoy this very successful conference here. So thank you very much again. So this presentation tends to be one of the regular papers we submitted to the conference, and in fact was done mainly by a graduate student, Jian Gong. I will tell you where he is right now, but let me try to hide it as a secret from this process. So the focus here is looking at something called resilience, and this is a very interesting topic because in our community in general, especially process control community, started looking at resilience back in 1970s or 1980s. But here we try to see how can we look into this problem from a different perspective, looking from a design and synthesis perspective, how this resilience could help us to design a better system. So many of you have probably seen things like this, that our chemical process systems are exposed to a variety of risks of disruptive events. This could be hurricane, could be earthquake, could be tsunami, or even some kind of cyber attacks and breakdown. So there are clear evidence showing that these disruptive events could lead to critical damages and disruptions to processes. For example, 1 year ago, Hurricane Harvey visited the Gulf Coast of the United States, and it damaged about 10% of the nationwide petroleum refinery capacity. It took more than 4 months to fully recover from this hurricane. Early this year, one of the very large liquefied natural gas plants in South Asia, owned by ExxonMobil, was completely shut down and damaged due to an earthquake layer. And it took almost 3 months for them to recover from this earthquake. So all these disruptive events have something similar in a way they first cause disruption, then it lead to some sort of loss of performance and some of economic performance. So the question we want to ask is, how can we design and operate this chemical process against these disruptive events? Or how can we make our system to be more resilient? In this particular case, we need to deal with 2 aspects. First of them is we want to absorb the impacts from all these disruptive events and absorb the impacts from all these uncertain cases. And the second issue or second aspect, which is quite important also, is to recover quickly from all these damages. So towards the very comprehensive resilience process systems, there are 3 major research challenges we need to address in this work. The first one is how can we quantify resilience? We need to find a quantitative measure for resilience before we can conduct any kind of systems analysis and systems design. So in particular, this kind of resilience metrics should account for a variety of factors, such as performance degradation, systems recovery issues, and also more importantly, from chemical engineering perspective, the multiple species and streams in the process systems. And there could be a variety of algebraic operations involved in the calculation and analysis. The second challenge is how can we develop a holistic and integrated optimization framework to account for a variety of design operational decisions, to incorporate the quantitative metrics for resilience, and also to account for many possible resilience enhancement strategies, which are very important, and we'll get into this in details in the next few minutes. And the last issue, which many of you have heard about, is how can we adjust the computational challenge to avoid our computer to go on fire like this. So towards these 3 research challenges, the normal contributions of this work involve 3 perspectives. The first one is we propose first of its kind, one of the interesting quantitative metrics for resilience for process systems. This should be particularly suitable for the design and long-term planning of chemical processes. The second contribution is we propose a normal modeling framework that accounts for economics, performance, and also account for resilience through a multi-level adaptive robust optimization approach. And the third contribution is a novel and efficient computation algorithm that could help to solve all these problems in a few minutes. So let's go into these topics one by one. Let's first talk about this quantitative measure for resilience. How it looks like after we have a disruptive event, or how it looks like after we have some sort of damage to our system. So the figure here shows more like a performance curve that you could typically see in any system we're talking about. The x-axis will change with time, and the y-axis is so-called system's performance. So when the system is under the normal condition, the performance will be somehow flat, always under small disturbance, which is given at the beginning of this time period. But let's say in time t, we have certain disruptive events, such as hurricane or earthquake or any kind of events. And then the system's performance will degrade over time, and this is because of the absorption of impacts we have throughout the process. Then by time t1, after the impact propagation phase, the system will try to recover because of our maintenance and operating phase. So after the system's recover phase, eventually it will resume to the normal operations and going through over the time. So this is so-called a systems performance curve or the performance degradation curve and recovery curve throughout some sort of resilience measurement. So there are many existing publications looking at resilience, but most of them, if you're looking at the design phase, will be more in the civil engineering, in the construction engineering community. And one of the most well-known, most acceptable metrics for this kind of performance is looking at a ratio of these two areas. The first area is essentially this blue box here. What it means is if the system is running under the normal condition or could fully absorb all the impacts and damages, then how the system's performance will change over time is an aggregation over this rectangle area. And this is given as the denominator at the bottom here. The other value, which is given at the numerator here, is looking at this area under the red curves. And this is the real performance over time for this system after the disruptions. So the way we quantify resilience based on this particular definition is looking at a ratio between the red area here and the overall rectangle area. So it's not surprising that if a system is fully resilient, then the resilience value will be exactly equal to 1. And of course, the worst case is after a disruption, the system will perform to the bottom and will not be able to recover over time. And in that case, resilience will be 0. But in most cases, you can see resilience should be some value between 0 and 1. So how will these metrics be translated into our chemical engineering community or process engineering community in particular? So for most process systems, it's very much consisted by a variety of process units. And this unit could be a single reactor or some decision columns or any kind of unit operational equipment units. So for each specific unit, there could be two modes. There's something we call stepwise change, which people typically use in dynamic programming, is that either the unit is operating, then it works. Or the unit fails, then it doesn't work. So by looking into this approach, what it means is we could really discretize the performance or discretize the capacity of each unit. And consequently, we could look into this performance curve change time with some of step functions. So with the help of these step functions, we could eventually translate the integral or integration into some sort of summations over time. And this is the way we could translate the resilience metrics to be more process engineering oriented and systems engineering oriented to look into this quantification approach. The next aspect is something about resilience enhancement strategy that I mentioned earlier, and this is indeed a main difference between a conventional process design that look into economics, look into sustainability, look into all sorts of impacts versus the resilience in certain process systems. So there are a number of approaches to enhance the resilience of a given system, but most of them will not apply simultaneously or holistically, as you can see in this work. So specifically in this particular contribution, we're looking into the 5 resilience enhancement strategies, namely optimal design, extra capacity, parallel units, backup units, and optimal operating levels. So we get into these one by one in the next few minutes, although some of them sound very trivial from a mathematical perspective. They are indeed widely applied in industrial practice. So the first one is called optimal design, and it's not surprising that once we want to design a process systems, we want to make sure it's optimal. And optimal has many implications. It really depends on what kind of objective we are looking for. In this particular case here, we can start looking into economics, but also you could look into the case that is most resilient or something that could recover the most quickly. So this would essentially imply that we could look into design that could give us the shortest recovery time for completing the same task. And that being said, there could be multiple options or multiple pathways for us to complete the same task. So there are some trade-offs involved in this case. And the way you could model it is to introduce some sort of binary 0-1 variables to indicate the selection of units and selection of pathways. And that being said, all these design decisions have to be made here and now. So these are for a first decision before any disruptive events or before any kind of uncertain disruptions is observed. Second strategy, which sounds also very interesting and relevant, is to increase the capacity of process units. And it goes without saying that if you have some sort of pathway like this, with the feed stock going here, and you can go through producing product 1 or producing product 2. So if we increase the capacity of the second unit, then in the case the first unit is disrupted or damaged, the second unit could still absorb and convert all the fixed stock into the products, although it could be a different product in this case. And the modeling is also very simple in the way you could look into some sort of BN constraints to capture the material flows in this strategy. The strategy 3 is the parallel unit, and essentially this is another way to introduce redundancy. So for instance, we could have a large decision column, a separation unit to complete a separation task. Alternatively, we could separate the capacity into two smaller units. And with these two smaller units, they could somehow enhance the resilience in case that if only one unit is disrupted or damaged, then the other one could be still working. On the other aspect, if all these units are damaged, then recovering one of them and recovering half of its capacity will be faster and more efficient than recovering everything we want to handle. So again, the modeling is trivial in the way that we could try to introduce some sort of inequalities and BN constraints to model this parallel unit strategy. The fourth one is one of another approach to introduce redundancy to the unit, and this is something you probably see quite often in industrial practice. For instance, we usually have something called backup pumps to capture all the possible disruptions of the transfer of liquid systems. For instance, you get a feed, you get a product, and going through one of the pumps. So if one pump is disrupted, then you can quickly have the backup pump to recover it and handle this fluid transfer task. So the modeling will be given as the ratio for backup capacity and the number of available processes in the equations here. The last strategy, which is something called optimal operating units, would essentially look into the best worst case. So looking at, let's say we have a simple flow sheet like this with a reactor and a few separation units. Then if one of them is failed and the other one is working, then the overall flow for the entire system can only take the one that has the minimum capacity throughout the process. And keep in mind, we have multiple species involved in these streams. So this is one of the unique features for chemical engineering process systems. Another noted feature is that this problem will involve the second decisions because we will never know the real operating units until we observe all the possible events. So this will be somehow like wait and see decisions that we can look into in the later phase. So after we have all these resilience enhancement strategies and the quantitative metrics for resilience, we can incorporate them into a holistic systems analysis and optimization framework for resilience. And overall, this framework, as you can see in the figure here, involves three major steps. The first step is to identify disruptive events, which is somehow going through the primary risk analysis and risk assessment, as we typically do in a chemical process design. And in the second phase, we develop this multi-stage optimization model, and the third one is looking into the solution and applications. So in terms of primary risk assessment, this is probably something you have seen quite often when we conduct this industrial process design. In certain way, we even looking into the probability of these disruptive events or looking into the degree or severity of these events. You could generally classify them into three different categories: low risk, moderate risk, and a high risk case. And in this particular case here, we only deal with the high risk and moderate risk case. Because for the low risk situations, we could most likely handle them through regular disturbance, and our control system should be able to balance them and recover the system automatically. After we conduct all this primary risk assessment, the next step is to develop a modeling framework and integrate optimization strategies. There are a number of methods, as you may know, that could handle uncertainty in systematic optimization approach. This could be sensitivity analysis, could be stochastic programming, or could be robust optimization. Sensitivity analysis is nice in the way that once you change the input to a certain degree of uncertainty, you will automatically change the output. But the drawback is that this is pretty much a post-optimization approach, which is hard to incorporate it in the design phase. Stochastic programming aims to optimize the expected value. The major advantage is that it could handle all the probability distributions very nicely. But the drawback, on one hand, is we cannot identify the probability distribution very rigorously or very accurately for all the disruptive events. And the second issue is handling a large number of scenarios could be very challenging. So the third approach, which has gained a lot of popularity, and we see a lot of talks in this conference about robust optimization. The advantage here is using the uncertainty set to model these uncertainty informations, and the decision will be made based on the best worst case. So the major winnings of this approach is that we end up with these minimax or multi-level optimization problem, which will be typically non-convex and non-linear. It could be challenging to solve. So just to give you a little bit more information about robust optimization in case that you have never seen before or never heard about it. So we say if we have a function, let's say it's a non-convex function following this kind of profile like this, a nominal optimization approach is pretty much the same as you put a ball and loading down a hill. So in this case, if the ball starts from here, P0, you're loading down the hill and it gives you the optimal solution, minimum solution over here. And this is one of the local optimal solution. In this particular solution, you're looking at absolute value and you assume all the parameters are deterministic or without uncertainty. And from sensitivity perspective, what you can see here is that compare this point versus this point, The other one probably have a little bit higher value, but it tends to be more resilient or more robust against any perturbations of the parameters. So in terms of robust optimization, instead of looking at a single point, we first define something called uncertainty set. And with this uncertainty set, the point is no longer a single point, it becomes a disk. And this disk is again defined by the region of uncertainty set. And the way you run the optimization is you play this disk throughout the profile. So once the disk is rolling down the file, what you can see is it doesn't really get trapped in this local optima or in certain way that is very sensitive or stiff to both perturbations. Instead, you choose the other solutions over here. So this is what we can argue here. Robust optima is somehow the case looking into the best worst case. And I do want to point out that this best worst case is exactly something that we are looking for in resilience. So some of you probably have seen something like this. We call it suspension bridge. So this was one of the real movie taken from this Tacoma Nano Bridge. At that moment, it was about built almost 100 years ago in the state of Washington, and at the time it was the third largest suspension bridge in the world. I mean, after Golden Gate Bridge and the Long Island Bridge in the US. But the bridge was not designed in a very resilient way, such that it collapsed 3 months after the construction. So what you can see here is the bridge is perturbating, dealing with all these disruptions and all these disturbance. But what we want to do, essentially, is to find out a case that will perform best under the worst case realizations. So this is one of the illustrations to show you that robust optimization could be a suitable approach to looking into the resilience optimization of a given process systems. And this is the concept that we have been learned from our colleagues in civil engineering and construction engineering. So moving forward, we are looking into this resilience optimization in order to balance a variety of issues, and more importantly is to hedge against the worst case realization. So this is indeed a sequential making process. We need to make the first decisions, essentially all the design and network connectivity decisions, and after uncertainty reviews, we made a second stage decision, or all operating decisions. So all this approach could be formulated in a min-max mini form, and end up using something called two-stage adaptive robust optimization. So mathematically, this approach could be written in a general form like this. We have X given as the here and now decision. We get Y, which are more like wait and see decisions, such as the material flows, operating levels, as I mentioned earlier, and uncertainty realized before the wait and see decision and after the here and now decisions. So this approach tends to be very suitable because it could well represent the sequential decision-making process we use in chemical process design, but also these recourse decisions could help us to adjust possible feasibility issues. So for this particular case here, we have two objective functions to look into. One is looking at resilience, and as we mentioned earlier, we can use a two-stage adaptive robust optimization looking into max, min-max case. The other objective is we try to minimize the total cost. So this was subject to a variety of constraints, such as network configuration, technology capacity, capital cost evaluation. And for this particular case of resilience metrics, as we mentioned earlier, we had to deal with some sort of robustness and disturbance. So this should be given as a min-max case here, and further account for all the first decisions that are made here and now. And after disruptive events, we have looked into uncertainty constraints, and further account for issues on recovery, all the linking constraints, and most importantly, the mass balance constraints. And all this second part here will be considered as a second stage problems or second stage optimization framework. So this is the overall idea of this multi-objective or bi-objective adaptive robust optimization for resilience analysis and optimization. So the uncertainty set is one of the key issues to describe uncertainty in this case here. And what we use is something called process unit of variability to capture uncertainty. And this is something that we don't know yet, but after the occurrence of disruptive events, we will have a better understanding and accurate count. So this uncertainty set that we introduce would follow a typical budget-based uncertainty set, but involve an objective component in terms of number of failed units, and a subjective component in terms of the tolerance levels that we could handle based on this specific case here. So moving forward is that you could write out equations. And again, how these equations do not really scare you too much, because this is our systems community, a typical approach. So what you can see here is we have some first decisions for network configuration, and then we have the first decisions also for technological capacity, followed by economic evaluations. And all these equations are pretty much made here and now before we design a process and before we see any uncertainty or disruptive events. Then we have a second decision looking into the recovery, looking into the linking values, and looking into mass balance and capacity issues. So this is the overall modeling framework in terms of constraints and in terms of the other first and second stage decisions. In terms of objectives, as we mentioned earlier, the resilience matrix will be given as a ratio form under this kind of real performance value over time divided by the ideal or the theoretical performance over time under the normal conditions. And this will be given as a max, min, max form. The other objective, looking at the total cost in terms of economic performance, will be given as a mixed integer linear form. So both objective functions in this case would reflect the interim properties of the process system that we are studying. And this will be a unique feature for this particular framework. So the next issue we need to talk about very briefly is how to solve this problem. As we mentioned earlier, robust optimization is very powerful and is very efficient to capture all the uncertainties and could be useful in this particular framework. But the challenge is on its solution. How can we solve something that with 3 operators, max, min, and max? And this is one of the challenges. The second challenge is we have 2 objective functions. So one thing we could do, well, sorry, this is x belongs to the real value. I think for whatever reason the computer did not display it. We could use something called epsilon constraint measure to transfer one of the objectives to the constraint. And this is something very straightforward. So after you make the transfer, it becomes a single objective problem. But still, this single objective problem is pretty much a multi-level problem, kind of nested, 3 levels nested all around. And then it's also involved with nonlinear terms and also fractional terms in both the numerator and denominator. So this problem tends to be very computationally challenging, multi-level optimization, mixed integer nonlinear optimization in particular. So it could not be solved directly using any off-the-shelf optimization solvers, and this non-convex problem really needs some sort of global optimization algorithm to guarantee the solution quality. So let me spend a couple minutes to show you how this approach could be tackled by investigating fundamental theory and algorithms in mathematical programming. So first thing we can observe is on this fractional term here. And this was borrowing around from an earlier series by Bengal batch back in 1970s, but also some studies in my group in a few years looking into kind of parametric algorithm. The main idea is what you can show is for any mixed integer fractional problem like this, given as a ratio of 2 functions, you could look into its parametric subproblem. And this parametric subproblem is pretty much nothing but an embedded optimization problem by introducing parameter q and then making it as a minimization of numerator here minus q multiplied by denominator here. So fq here is exactly a function, but it doesn't have an explicit algebraic form. The thing that we could prove is that if we could find the value of q such that this function fq will be equal to 0. Essentially, if you optimize this problem, solving this single level optimization by minimizing this n minus q multiplied by d with objective optimal zero equal to 0, then the solution to this problem will be exactly the same as the global optimal solution to the original one. So that's exactly what the theory is all about. And we can further prove that this function fq, although it doesn't have an analytical form, it has a very interesting property that it's concave, it's continuous, it's monotonically decreasing, has a unique solution when fq equals to 0, and then also the subgradient for any value will be the negative of the denominator. So these results were presented, I think 2 or 3 years ago back in PSC in Denmark. So with these properties, we could really try to design an algorithm using a numerical root finding measures. We start from initial guess and then try to take these subgradients. Each time we solve this inner problem, we get an objective value and also a subgradient for free. So you can iteratively solving it until eventually you can reach out to the optimal after certain iterations. So once we have this parametric algorithm, we introduce solving a sequence of subproblems and iteratively eventually we get optimal. And one of the most powerful features here is that each subproblem does not need to be solved to global optimal. Instead, one of the interesting theory we introduce is once you can solve these subproblems to any feasible solution that is within 100% global optimality gap, it will be good to move forward and eventually guarantee to converge to a global optimal solution. And this is something we call init-z, Newton's measure, for applying to this problem. And there's a very powerful approach they could apply to any kind of convex, non-convex problems, even these multi-level optimized problems. So we're going to embed this approach into the framework we are dealing with, max, min, max problem with fractional term. We're looking into the parametric subproblem and eventually take these steps and solving into global optimal. So the key idea in this case here is that each subproblem will end up with a 2-stage adaptive robust optimization problem with mixed integer linear problems within the problem here. So all we do is follow using a low and column generation algorithms by decomposing into a master problem and a subproblem, and iteratively solving them by adding optimality cuts and feasibility cuts until eventually the solution is converged. So the main idea is through this partial enumeration of all the extreme points in the inner problem, and eventually convert this multi-level ARO problem into a single level one. So this is how the entire algorithm framework was showing about, and in fact was applied to an earlier work looking into the LG process network under uncertainty, published by the same student early last year. So our framework is like this. We have an outer loop looking into this parametric algorithm, and we have inner loop looking into this row and column generation algorithm to guarantee the convergence of global optimality. So that's the end of the theory. Let's see how this approach could be useful and could be applied to some of the real applications we usually talk about. So first, looking into some kind of typical process network problem taken from earlier work by Professor Grossman and others, where classical approach we have been looking into in our community. So this is a process network involves 6 process units, 1, 2, 3, 4, 5, 6, as you see the numbers here. And there are 4 fixed dots, as you can see over here as well, and plus 6 final products. So we try to see under the disruptions how these chemical process systems will perform and how the resilience will look like. So first thing is, how can we solve this problem? I mean, the solving this problem is not trivial, but certainly with the algorithm I mentioned earlier, what you can see is getting all these solution sub-problems in generally takes 1 minute or at most 2 minutes. So this really shows the power of theory and algorithms. Once you know how to tackle the problem, they could be handled in a very effective way. But further, once you look into this problem itself, you do see some multiple parallel optimal curves. So essentially, x-axis shows the economic objective, and y-axis shows the resilience. So as I mentioned earlier, resilience is defined as a ratio, so it's between 0 and 1. For any process, once you design it without considering resilience, it does still involve some sort of resilience. And that's what you have in the left-hand side here. For some of these designs, even you don't really expressly design them to optimize the resilience, the optimal design, by minimizing the cost, already give you certain resilience. And certainly this value of resilience will depending on the specific disruptive events that we want to hedge against with. For instance, in the blue curve here, it's for a case that once you have a disruptive event, they could fail 2 of your processes, 2 out of the 6 processes. Then the current design, the optimal design we get, will give us about 70% resilience, even though we don't really optimize it. But certainly, you could try to invest more by looking into all these resilience enhancement strategies, introducing redundancy, optimize the design, optimize the operating levels, to eventually improve resilience from around 70% all the way up to 100%. But the price you pay, as you can see from the figure here, is we had to increase the cost, almost double them throughout the process. Similarly, if you're comparing these different curves around on the curve here, at different levels of disruptive events, from the most kind of say mild event to the most serious event, this particular resilience variable will decrease. However, the ultimate solution with the full backup units and full redundancy will always give you 100% resilience in the maximum cost, investment cost. Another issue I do want to introduce here is you can see 2 curves that are pretty much overlapping with each other, the blue one and the yellow one. So the yellow one is for the case that the full failed process will be failed under serious disruptions. And the green one is the case that you have 2 disruptions in sequence. Maybe you get a hurricane and then come up with a tsunami. So one of them will damage 3 processes and the other one damage 2 processes. It turns out that for this particular process system, because of its network structure and its design, these 2 curves exactly overlap with each other. So what specifically do they look like? So here are the solutions. As we mentioned earlier, A, B, C, D are 4 possible solutions. And each of these solutions will end up with different designs. So in particular, solution A, B, and D will end up with the same design like this. And what you can see is only process 3 is not selected, but all the others were selected to design. And then in solution C, it turns out to come up with all the processes online. But in addition to this conventional design, we also need to look into all these redundancies and backup units. So the figures here shows you the capital cost for each process and each possible solutions. So what you can see is in the solution A, which is the minimum cost solution, we just build all the process we need, and that's it. We don't really introduce the redundancy. In solution B, which increase the redundancy slightly, what you could have is a little bit orange bar here. Essentially for process 4, we have a little bit redundancy units, and with a smaller capacity to hedge against uncertainty. And certainly the system identified process 4 over here, it's one of the most vulnerable process that has to be protected against all disruptions. And then once you increase the resilience, you get to see a bit more redundancy on process 4 and also a little bit on process 5. Then in the last solution here, with the solution with all the full redundancy case, essentially all the processes have backup units. Process 1, 2, 4, 5, 6 all have backup units just to hedge against the uncertainty. And this will be translated into the performance recovery curve, as you can see on the right-hand side here. Let's say in the first case, if you don't introduce any redundancy, after disruption, the productivity will reduce, and then it takes some time to recover over the period. In the second case, because you do have a backup unit, so after the disruption, the process performance was not fully damaged. Instead, it was slightly damaged, but not that much, so recovery becomes much faster in this particular case. And third case will be more optimistic. In the last case, because we have backup units for each of them, the system was fully against all the possible disruptions under the existing process units. So if you revisit all the resilience enhancement strategies that we mentioned earlier, what you can see is in all these 4 designs, we choose both optimal design and also optimal operating levels. But of course, operating levels will be different based on the specific design we choose. In addition, extra capacity and parallel units turns out to be not so optimal, at least from the decisions we are choosing here and from a specific problem. However, backup unit is something we do choose as one of the most effective strategies. For instance, in point B, we have 1 backup unit, but not in the full capacity. In process C, similar but slightly larger capacity, but in process D, we end up with all the process with 4 backups. So further is looking to some sort of more important applications in one of the industrial shale gas process systems. And this is one of the cases that you're looking into raw shale gas and going through a number of acid gas removal, dehydration, and eventually separating pipeline quality gas, natural gas liquids, and sulfurs. So there are a variety of technology options and process design alternatives with about 108 design alternatives in the case. The overall superstructure looks like this, which involve a lot of detailed process units that I don't want to get into details. So very similarly, is you can end up with a Pareto curve to reveal the trade-off between economics and the resilience. And again, the resilience will range between 0 and 1, but for the case that does not really account for resilience in optimization phase, the original resilience at the starting point is about 40%. But certainly you can try to increase the capital more than double to make it almost 100% resilient against any disruptive events. So the optimal choice here, we end up with starting from raw shale gas, and then choose DGA for absorption, acid gas removal, and go through the condensation, eventually looking to integrate the natural gas liquid recovery and separation process. So looking into these worst case realizations, what you can see is there are a few solutions we call E, F, G, H. So again, keep in mind E is the one with the minimum cost, and H is the case with the maximum resilience. So the main difference here is in the case E, after disruption, the performance decreased to 0 right away. But it takes some time for everything to recover and fully go back online. But for the case of H, because we have sufficient backups and redundancy, after disruption, nothing will be affected, and we can keep moving on with the same process to ensure 100% resilience in this specific realization. So let's revisit another thing is the resilience enhancement strategy. Again, optimal design, operating levels are the same for all these designs, and these are always something we have to follow. Backup units were selected for some of the solutions, the last 2, but not all of them. While in the second case here, we tend to choose parallel units for all the processes to maintain the resilience. So this really shows the trade-off between all the resilience enhancement strategies. It's hard to say which one is more important. Maybe optimal design, operating levels are always essential. But among the 3 of them, actual capacity, parallel units, and backup units, they have pros and cons. And the system or this framework could automatically select the optimal one based on a specific design and synthesis task. So last thing is about the computational performance. As we mentioned earlier, our algorithm is pretty much a combination of parametric algorithm and a low and column generation algorithm. So in a low and column generation algorithm, we produce upper bound and lower bound in each iteration, and they keep going on until eventually converge. So we have to go through these 2 steps for a parametric algorithm, starting from initial value of 0 and come up with the optimal value of 700 or something, and then we put it into the original problem and resolve it, and end up with a parametric value equal to 0. Which really gives you the global optimal in the end. So let me conclude. We have a very nice framework in this case that offer an alternative perspective for design and operating a process systems from a resilience perspectives. And so then this is not the same with most of the existing resilience concepts we use in process control, but alternatively offer an interesting perspective looking at this problem from a design and synthesis perspective. So I do want to acknowledge the student who worked on this project, which is Jian Gong, who just received his PhD a few months ago. And sometimes you do see this issue that we haven't really found a direct application in chemical industry for this framework. Nevertheless, some of our financial competitors just quickly grab him, and of course, he is making a lot of money right now. So this is probably one of the issues that we are facing in our community, how to retain and attract our very best students to continue in our community and working on very interesting and important problems. So with this, I want to thank you very much for your attention. I want to thank you again for all the organizers for the opportunity to present here. And I do want to show you the very beautiful campus we have in Ithaca, New York. Cornell is one of the Ivy League institutions, as many of you know. But in particular, we have 4 major campuses that many of you probably don't know. Our main campus in Ithaca, New York, which is exactly on the top of the hill. And the hill is pretty much the same as the hill you see in Grass. Very beautiful, wonderful view. And I also have the lake here. And the clock tower is pretty much the same as you have here. The only difference is you put the entire campus on the top of the hill. So maybe next time when you want to expand your campus, the idea is go to the top of the hill to get a much better view for all of us people. And we have 12 waterfalls on campus as well. So definitely we welcome everyone to visit our campus. Our 4 campuses, by the way, it's one main campus in Ithaca, New York, and 2 other campuses in Manhattan, one in Uptown Manhattan Medical School, the other in Midtown Manhattan Tech Campus, and there's another campus in Qatar. So again, thank you very much, and I'll be happy to answer any question you may have.
Tony Kiss, University of Manchester. Thank you very much for the interesting presentation. I enjoyed the theoretical part and it looks great. Resilience is something that we do need in the chemical industry. But let me ask you a practical question from an industrial viewpoint. A key feature of your approach is having redundancy and backup units. When you have a disruption such as a hurricane and your whole plant is flooded and everything is underwater, how will your backup units function then?
Yes, very good question. That's exactly the key issue here. The backup unit is not a trivial backup unit that right next to it. Instead, it's really a backup unit that we want to put it in a certain shelter or some kind of events that would protect against all the hurricanes. For instance, the backup unit could be something in a warehouse or in any particular facilities that could hedge against the hurricane or flooding case. So in the end, that's what you can see. The backup unit tends to be much more expensive than the regular units you have.
Okay, next question.
Thank you. Thank you for this great presentation. You showed this risk assessment matrix at the beginning, and you showed the probability on the one and the impact on the other side. You're dealing here with scenarios that have a very low probability, at least in this region here, probably it's a little bit higher in the south of the US.
Right.
But still, it's a very low probability
Exactly.
with an extreme impact.
Right.
How do you deal with the quality of the figures that you need to evaluate what is now really the probability that you have? Is it once in 1,000 years? Is it once in 10,000, 100,000 years? Will probably have a significant impact on your results.
Yes, excellent question. And this was exactly the motivation. Well, I think the question is really about getting the probability of these disruptive events. And this is exactly the issue that we did not go with the stochastic programming approach. Because if you don't run with stochastic programming, you want to come up with the accurate probability distribution of these disruptive events. Instead, in this case, we use robust optimization, which doesn't really account for the exact probability. That being said, I understand that your concern is pretty much saying that if in this area, let's say in Grass, beautiful city, peaceful, we don't really worry about hurricane, we don't really worry about earthquake. Why do we need to care about these things? Well, I would say there are 2 perspectives. First, do you really need to have a process that is so safe and so resilient? If yes, you will be willing to understand and invest more. But more important is we call this framework resilience analysis and optimization. So optimization is an add-on, but not necessary. And this is exactly in the issue here, what you can see. Even you design a process without accounting for resilience, we understand how much is resilient against all the events. And that could at least give decision makers some kind of guidance. It's the same as we choosing a car. Do you want to come up with a sedan? You want to come with buy a SUV, or you can go with a Rolls-Royce? You know, it's all our personal decisions. But at least this is a framework to help us to quantify how the existing system could hedge against all the possible outcomes, if one wishes.
Yeah, thank you for a very interesting presentation. This is a little bit of a follow-up of the two previous questions, because in the end, the resilience, obviously, it can be translated into cost, because if your plant is not resilient, to get started, the loss of production, etc., and then you would have a similar basis to analyze it, because if you have the 1,000-year, and I think a resilience of 0.7 may be good enough, while if it's much more often, you may need 0.9 or
yep.
0.9. So have you considered looking at it from that perspective?
Exactly. So I think so. So there are two aspects we could look into. Right? For instance, if you are building a plant in Gulf Coast, let's say in Houston area, you get to see hurricane almost every year. Then you can use really a data-driven approach to come up with some sort of uncertainty set or quantify information. In certain areas, let's say Fukushima in Japan, which is a very nice example, they look into these events every hundreds of years. Then you could really look into resilience in a way that, for the decision maker's perspective, are we willing to invest, doubling the investment, just to avoid all these public disasters? If the answer is yes, then we would do it. But I bet in most cases, if it's an individual organization or private organization, they will most likely go with this value. But the key idea of this approach is to show them that even if we go with the optimal design in a conventional way, resilience is not zero. It's not too bad, but it's not so good. So if someone is willing to enhance the resilience over the course, then you probably have to double the investment. And this is very much consistent with all you can see in all these kind of disaster events.
Okay, thank you for your presentation. I'm João from Technic in Lisbon. And we can increase resilience both for robustness or due to flexibility to redundancy. But that makes us always making something on the assumption of a disruption. Mm-hmm. And how can we manage risks that might be known unknown or even unknown? Do you have any suggestion to make a broader and in terms of supply chain or process to deal with this latter term of resilience? Thank you.
Yeah, thank you for the question. I guess an easy answer to your question was really about this figure. It's exactly the case when they build the bridge, they did not really account for all the things they should think about, and eventually cause the disaster. So in the end, I would say this is really much a decision maker's perspective. They need to balance all kind of factors, and getting data is indeed difficult. That's why in the end, we don't really go directly with the probability approach, because in that case, you require a lot of accurate information. Instead, we are looking into our systems itself, looking into the process system itself as a physical condition, and see how these conditions could be enhanced and could be modified, at least to avoid some kind of catastrophic disasters like this case here. But certainly the framework, I mean, as what we are speaking now, is that we could extend it to looking into supply chain resilience. We could apply it to nationwide economic systems. We can also apply it to global econ systems, looking at the sustainability perspective. So there are a variety of perspectives to extend this framework through some kind of customization, modification to adjust a variety of applications at different scales and at different levels.
In the sake of time, we have to stop now. If there are questions, we have another coffee break and a short poster session at the very end of the day. I suggest to thank Professor Yu again for his
Thank you very much.